Today we're going to talk about equations of motion for constant acceleration. Now we're saying constant acceleration because throughout this course we're going to consider acceleration to be constant. Considering it to be constant does not mean that acceleration is always constant in real life. Actually, most of the time, acceleration is not constant in our day-to-day lives. When a car is moving from one position to another and it speeds up and it slows down, that acceleration and deceleration is practically not constant. And most motion in the universe really is not constant acceleration. Acceleration is non-uniform. But for simplicity, we're going to, and for the purpose of trying to understand the ideas, we're going to consider acceleration to be constant throughout this course. Some popular examples where acceleration is obviously not constant, where it's non-uniform, is when a rocket is being launched. That's non-uniform acceleration. But like I said, for this course, we'll consider acceleration to be constant. Now, before we go on, before we get these equations, because these equations will help us be able to predict the motion. If we have a set of equations where we can just plug in known information to get unknown information, will help us to analyze motion of objects easier. So before we get there, we're going to need some notation that's agreed on. So for example, if I'm talking about time, I should be able to write t, and not a vector quantity, I should be able to write t, and everyone will know when they see me write t that means time. If I use t and someone else uses x and someone uses m for time, there's confusion. So the agreed notation, the most common notation for these equations of motion is that time is delta t. Remember, time changes, yes, but since usually the changes from an initial value to a final value, since initially the t naught is considered to be 0, we're just going to use t always as our time symbol. Velocity also changes, and the change in velocity is v1 minus v0, where v0 is initial velocity and v1 is final velocity. Displacement also changes. Change in displacement will be denoted by x1 minus x0. Now it's going to help you to write through these things, take notes, because it will help you understand better. But it's not a must that you should write notes. And I said acceleration at the beginning, we're going to consider acceleration to be constant. So we won't be having any changes in acceleration. We're just going to be using a symbol a. It's a vector quantity. Now, to form these equations are coming from the basic ideas that we have about motion. We know for sure that velocity is the rate of change of displacement. We know that. Rate of change of displacement. So since velocity is the rate of change of displacement, then v will be change in x divided by time. If I substitute for what I know change in displacement to be, this will be x1 minus x0, all divided by time. And if I rearrange this, I get vt, when that crosses over, is equal to x1 minus x0. So I have an equation for the final position of an object being x1 is equal to x0 plus v0 times t. So that's the equation, and this is the first equation of motion. It's the equation for the final position of an object. If I know the initial position of an object, I know its speed and its time, I can predict using this equation by simply plugging in numbers where that object is going to be, right? If I was told that Georgie was initially at a position of 6 meters, and he traveled, he traveled at a speed of 0.2 meters per second. This is very slow, Georgie. 0.2 meters per second, and it took him 3 minutes to get to where he was going, and I want to know his final position. Then I can plug those values straight into the equation, and that will tell me where George is going to end up. So George's final position according to this equation would be x, x naught, which is 6, plus v naught, which is 0.2. Sorry, this should just be v, not v naught. V, velocity. V, which is 0.2, times the time, which is 3 minutes, but changed to seconds. So 3 times 60, change it to seconds, and this should give me George's final position in meters. You guys can work that out. Alright, so that's the first equation of motion. Now, moving on, the other definition, the other obvious definition that we know is that acceleration is the rate of change of velocity. So acceleration is change in velocity divided by time. That means that acceleration is v1 minus v0 divided by t, which when you rearrange gives you v1 equals v0 plus at. Again, this is looking very similar to the previous one, and it's the second equation, where if I know an object's initial velocity, if I know its acceleration, and I know how long it traveled for, I can use that information to find its final velocity. Or if I know the final velocity and the time, I can find its initial velocity. We'll do practice examples about these things in a little bit. All right. So the other idea that we know is that total displacement, the total displacement of something, will be given by the average velocity multiplied by the time. To put this in perspective, if you leave Heritage and you go to your house, maybe your house is in Makindye, there is no way that you're going to travel at a constant speed or at a constant velocity because of how the road moves and because of traffic and because of all that. Your velocity time graph is going to, look funny. But when someone asks you what is the average speed from Heritage to your house, average velocity from Heritage to your house, and you give him a value, say 20 kilometers per hour, that doesn't mean that you travel at 20 kilometers per hour from the time you leave the gate to the time you reach your house. There's acceleration, deceleration in between. There's even sometimes when you're stopping. So the clearest picture for you to give that you will give that person will be that my average velocity is the total displacement I moved, total displacement divided by the total time. And this is really how we calculate average speed and average velocity. So this tells me that total displacement, because if I just cross multiply, if I cross multiply, this will tell you that total displacement is average speed or average velocity times time. I really should be saying average velocity, not speed. So we know total displacement, which is x, is going to be equal to average velocity times time. Average velocity, if it's trying to compute the average velocity between 2 points, when a car has 2 different speeds and you want to know what was its average, I just add up those velocities and divide them by 2. The initial and the final velocity, then I multiply that by time. Now this, as it is an equation of motion on its own. So that's the third equation of motion. Remember, this one over here was the second equation of motion, third equation of motion. So we can use these 2 equations of motion because if you look at them, the first equation of motion involves displacement, speed, and time, right? The second equation of motion involves velocity. Like I said, I should really be saying velocity instead of speed. Includes velocity, acceleration, and time. This one over here includes displacement, velocity, and time. What other combinations can we have? Let's see. Now from this equation, from the second equation that was v1 equals v0 plus AT. I hope you can see that I can substitute for V1. I can substitute for this V1 because this is V1. This whole thing is V1. I can substitute for it in this position. When I substitute for it there, I'll end up with displacement equals V0 plus V1, which is now V0 plus AT, everything over 2, everything multiplied by time. And when I simplify that, I'll have X displacement is equal to 2V0 T, when the T comes in, plus AT squared, all divided by 2, which you can break up into what it looks like there. So I'll have X is equal to V0 T plus half AT squared. That is another equation of motion. Alright, so one small thing though, this should have been a change in displacement all throughout, change in displacement, change in displacement. So because I know change in displacement is x1 minus x0 equals V0 T plus a half AT squared, then I hope you can see that final position is initial position plus V0 T plus a half AT squared. Really, in most cases, this is the one that we use, this one right here, without this component. But that component is still part of the equation. It's going to be very rare that you find, usually the initial position is considered as 0, but for accuracy and just so you see things that are consistent going forward, this is what the equation should look like. A change in displacement, the total displacement will be a change in displacement, should equal average velocity multiplied by the time. Alright, so there's one other form of equation. So from this equation, that V1, final velocity, equals initial velocity plus AT, we can again rearrange it in a different way. So if I was to square both sides, just doing some algebra for the sake of fun, if I square this side, and I also square this side, I'll have V1 squared equals V0 squared plus 2 V0 AT plus A squared T squared. Alright, so I have V1 squared equals V0 squared plus, now when you look at these two terms, I have some things that are common, and I can take them out in such a way that I get something that looks like this equation right here. So I'm trying to rearrange it in such a way that I can substitute for that. And you're going to see how that works out. So if I pull out A and T, if I pull out AT, I'll be left with, if I pull out A, I'll be left with 2V0 plus AT squared. Now, if I continue on and pull out a half, if I pull out a half, A over 2, I'll be left with V0 here. Sorry, if I pull out 2, if I pull out 2, not a half. If I pull out 2, I'll be left with V0 here plus half AT squared. Because if I were to multiply that 2 back inside, this will become 2V0, and this 2 with the half would go back to 1. So I've not changed anything. I've not changed the meaning of this equation. Now what I have here Let me just write it out here. Is V1 squared equals V0 squared plus 2A, open brackets, V0 plus half AC squared. That's what I have. And I hope you remember from this previous board that V0 T, where is the T? Oh yeah, I left out a T here, left out a T here. If you remember that V0 T plus a half AT squared, this whole bracket is equal to change in displacement. If you guys remember that. If you look at this right here, change in displacement is V0 T plus half AT squared. And if you look again here, I have V0 T, I keep forgetting that T, V0 T plus half AT squared. So that whole thing is change in displacement. And I'll end up with V1 squared equals V0 squared plus 2A times change in displacement. Now the good thing about these equations is that no one is going to require you to show how you, no one is going to require you, so no one will ever ask you to show that you know how to prove these equations, but it's very important that you know them and that you can get them from memory. They're also on your equation sheet, your AP equation sheet. So you can find them there. However, you should always remember them by memory. So if we just go through them, the first one was x1 equals x0 plus vt. The second one is v1 v0 plus at. And the third one was displacement is equal to v0 plus v1 out of 2 times t. The fourth one is again change displacement equals v0 t plus half at squared. This one can also be written as, because if you work out this change in displacement, it can be written as x0 plus v0 t plus half at squared. You will see this in your formula sheet. It's stated as this, but you know that the meaning is that it's coming from this change in displacement. And the last one is v1 squared equals v0 squared plus 2a change in displacement. So those are the 5 equations of motion. I hope you can practice how to derive them on your own, just so you get a very good understanding of how to use them. But like I said earlier, no one will ask you to prove them in an AP exam. Now, if you look at them, there's a quantity missing in each of them. We have 5 quantities. We have time, we have initial velocity, we have final velocity, acceleration, and displacement. And each equation has at least 3 of them. So this equation 1 has displacement, velocity, and time. Final velocity at least. Second equation has initial velocity, final velocity, acceleration, time. So it has velocity, acceleration, time. Now, depending on what question you're trying to solve, you're going to be looking for an equation that has what you need, or that has what you have, and the unknown is what you're looking for. In order to solve this equation, it's always nice to have 3 knowns. If you have 3 knowns, you can use one of the equations to find the unknown. So that's kind of the approach for solving equations of motion. Let's look at this example. You're driving at a speed of 20 meters per second. So that tells you that your initial speed is 20. It's nice to list out what you have so that you can select which equation will help you find what you don't have. So you are at a distance of 28 meters away from the tree when you hit the brakes. So your displacement is 28 meters. Assuming your vehicle does not skid, so that helps because you don't have to worry about the skidding distance. What is the minimum deceleration needed to avoid hitting the fallen tree? Now, there's given information here that is not stated and that is that your final speed is 0 meters per second, because you're going to decelerate to avoid hitting the tree. That means you're going to come to a stop, right? It even tells you here you come to a complete stop, so that means your final velocity is 0. We do not have the time, and we do not have the acceleration. So you have initial velocity, you have final velocity, you have displacement. Which of these 5 equations can you use to solve for acceleration? Can we use the first one? No, it doesn't have acceleration. This one has acceleration, but it doesn't have displacement, so we can't use that. This one has displacement, doesn't have acceleration. This one has displacement, it has acceleration, it has time, but it has so many unknowns for us because we don't have either time or acceleration. The best one to use in this case would be this one right here, because we have final velocity, we have initial velocity, we need acceleration, and we have displacement. So we're going to use the equation v1 squared equals v0 squared 2ax. v1 is 0, v0 is 20 squared plus 2 times acceleration times 28. And the only unknown in this equation is acceleration, which you can solve for. Please do not forget the units, meters per second squared. All right. Sorry, there was a part B. Part B, how long did you slam the brakes for? Now that you have the acceleration, you can calculate the delta t, the time, because it's the only unknown that you'll have. And you can use any of those equations really to solve for the t. You can use this one. I think it will be the fastest one. So yeah, you have acceleration, you have this, you have that. You're only finding time, so you can be able to just substitute and solve for t. Next one, person stands at the edge of a straight cliff 20 meters high. This is 20 meters. Hold the ball over the edge. The person tosses the ball directly upwards. They're standing here. They toss the ball upwards. The ball is going to come back down at an initial speed of 5 meters per second. So initial speed is 5 meters per second. And how long will it take the ball to hit the ground at the base of the cliff 20 meters below? Now in questions like this that involve falling either upwards or downwards, first of all, you know that acceleration is the acceleration due to gravity, but it's very important for you to choose your convention. What I mean is, choose for yourself which direction is positive. If you want up to be positive, then be consistent with what you've chosen. And if you want down to be positive, again, be consistent with what you've chosen. Now, naturally, we know the acceleration due to gravity is downwards, right? We know that downwards is acceleration due to gravity, which is 9.8 meters per second squared. So, if you choose up to be positive, that means your acceleration will be negative. But if you choose down to be positive, that means your initial velocity will be negative. So, according to me, I'm going to choose up as positive. As long as you stick with your convention, you will get the same answers depending whichever way you go. So my initial velocity is 5 meters per second. That means my acceleration is negative, 9.8 meters per second, because it's down, and down is negative. My displacement, where is this ball falling? Starting from here, remember it's displacement, it's not distance. I know it goes up there, yes, and it comes back down here, yes. But if displacement from this position to this position is simply 20 meters. So displacement, is it up or is it down? It's down, so my displacement will be negative. Now the one needs to figure out how long it will take to hit the base of the cliff 20 meters below. I have displacement, I have initial velocity, I have acceleration. The easiest method to use here is the fourth equation, which is x equals v0t Assuming displacement is v naught t plus half at squared. Change in displacement is negative 20. Initial velocity is 5. Time is what I want. Half times acceleration due to gravity, negative 9.8 times t squared. This is a quadratic equation which I can rearrange, and it will look like 4.9 t squared. You can do the math. 4.9 t squared minus 5t minus 20 equals 0. If I solve this quadratic equation, I'll get two values of time, and the value that's negative will be discarded, and I'll only consider the value as positive. Right, lastly, basketball is dropped. Again, we're dropping something, and it rebounds to a height of that. Assuming that ball is not moving horizontally, calculate its velocity just before it hits the floor. Again, height is 1 meter. It's rebounding to a height of 0.67. Again, I'm using down as negative and up as positive. So my change in displacement in the first case will be negative 1 meters. Acceleration due to gravity is negative 9.8 meters per second squared. I want to know its final velocity just before it hits the ground. Do I know its initial velocity? Yes, they told me it was dropped from rest. 0. So for now, I don't know how long it's going to take to hit the ground, but I can use the same equation, v1 squared equals v naught squared plus 2a delta x to find the final velocity. Final velocity squared equals v naught is 0 because it was at rest, 2 times negative 9.8 times negative 1. And my v1 will be the square root of 19.6. So you can work it out and find the final velocity just before it hits the ground. Now, you can use the same reasoning to find part B, just after it left the floor on the way up. Alright? And I'd like to see what you guys come up with on that. So this is going to be the first part of your homework. You'll also finish part C. So yeah, that's it. I'm going to assign you some homework on Google Classroom. Bye.